We'll continue with the module 5, material science. In the last class, we have seen the definitions of classical free electron theory and some classifications, that is insulators, semiconductors and good conductors, and relation between the electrical parameters such as current density, resistivity, etc. Then also we have seen the temperature dependence of electrical resistivity, merits of classical free electron theory, failures of classical electron theory. We have seen two failures, and introduction of quantum free electron theory, and also we have just see the assumptions. In the current lecture, that is part 3, we will see the definition for Fermi factor, that is f of E, and definition for Fermi energy, EF, that is one of the important definitions. And interesting topic is temperature dependence of Fermi energy, and Fermi temperature, definition for Fermi temperature, Fermi velocity, and the significance of Fermi energy. First, let us relook into the assumptions of quantum free electron theory. So, wherein let us just focus on the fourth and fifth. The fourth one is distribution of electrons in various allowed energy levels is controlled by a Pauli's exclusion principle, and fifth one is regarding the statistics. So that means Fermi-Dirac statistics, which is employed to estimate the probability of free electrons occupying a particular energy level. So that means from this one you see that it is not that all the energy levels will be there. There are only few allowed energy levels. So here what we see is the probability of occupation of these allowed energy levels. This is governed by mainly the Pauli's exclusion principle. So why we look into the specific or discrete energy level or the probability is because, and that will also help us to explain many of the failures in classical free electron theory. For example, in classical free electron theory, we had discrepancy in explaining certain physical properties, and specific heat is one of that, wherein experimentally determined specific heat is smaller than the theoretical one, which is considered using classical free electron theory. So hence we should look a little bit more closely into the statistical behavior of electron gas. Since they have, which is the electrons have a spin and obey Pauli's exclusion principle, they are called as fermions or Fermi-Dirac statistics. Students, we have been speaking about the probability of an electron occupying a given energy level, that is distribution of electrons of a real material among the available energy levels. Here you look into the energy level diagram. So this is what we call as energy level diagram, wherein here as we go up, so that means energy is going to increase. These are different, these blue lines are different energy levels. These are different energy levels. So as you go up, so that means energy is higher, 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 like this. And these lines are the allowed energy levels. So in between them, so that means in between them here, or let me take a different color, here or here, these are the forbidden energy values. These are the allowed energy values. So these lines are the allowed energy levels. Okay, now if you look into it, so that means electrons are going to start filling from the lower energy states, that we know by Ohm's rule. Also we know that it starts filling by the lower energy level. So first lower energy level is filled, then next higher level energy is filled, and then the next is filled, then the next higher level, then the next energy level is filled. Let me say that I am explaining these fillings at 0 Kelvin. Okay, so at 0 Kelvin, so this is what is written at 0 Kelvin. I am explaining the filling from the lower to the higher energy levels. It is being filled, and this is the highest energy level which is being filled at 0 Kelvin. So that energy level we call it as a Fermi energy level. Okay, so at 0 Kelvin, the energy levels which are below Fermi energy level, they are all filled energy levels, and for energy levels which are above Fermi energy level, which are above Fermi energy level, which are the vacant energy level. So this is, and the energy Fermi energy level or Fermi energy is represented as E suffix F. So let us explain what is Fermi energy. By definition, the Fermi energy level is the energy corresponding to the highest occupied level at absolute zero temperature is called, that is nothing but the Fermi energy level, and it is denoted by EF. Okay, so this is what we have already seen in the previous slides. I'm just giving you here some of the values of few elements. They are copper, silver and aluminum. For copper it is 7.05 eV Fermi energy. For silver it is 5.49, and for aluminum it is 11.63 EV. In this slide, let us try to understand the representation of Fermi factor in terms of graph or graphical representation. So here we are having the graph. So x-axis is the energy, as you could see, x-axis is the energy, and y-axis is the Fermi factor. Okay, that is F of E. Okay, so if you just look at this figure. So as the energy is increasing here, as the energy is increasing, the electron occupancy is going to increase, okay. So this is also going to increase. So that means it is going to increase till it reaches the Fermi energy level. So here also, as the energy is increased till Fermi energy level, that is EF, it is a filled part. So this is what we say as a filled part. Okay. So above EF in this part, the energy levels are vacant. That's all. And at which temperature we are explaining this? We are explaining this at 0 Kelvin. That is important to remember. In this slide, we are going to explain the same thing in another language, that is mathematical language, that you could see here. When E is less than EF, that implies F of E is 1. Okay, so that means E is less than, so that means in this region F of E is equal to 1. So that means it is, for sure it is filled. Okay, so it is filled here. Okay, so at E, that is greater than EF, so that means we are speaking here at greater than EF, F of E is equal to 0. So that means what is F of E? F of E is nothing but the probability of filling. Okay, so that is going to be 0. There is no filling, so that means it is vacant. And you could see here the energy levels are vacant. Okay, so that is what is expressed mathematically in this term. Fine. Now let us see the expression for F of E. Okay, which is a Fermi factor. Okay, so that is given by 1 over 1 plus e to the power e minus ef divided by kt. We don't have a derivation for this. You need to remember this equation. It is important. Okay, I'll repeat this. F of E is equal to 1 over 1 plus e to the power e minus ef divided by kt, where F of E is the Fermi function, E is the energy level whose occupancy A being considered, EF is a Fermi energy level, K is a Boltzmann constant, and T is a absolute temperature. Again, let us just refresh the definition for Fermi energy. So it is nothing but the energy corresponding to the highest occupied energy level at absolute zero. Okay. Okay, now the thing is why we should learn about EF, that is Fermi energy. The interesting part is electrons above EF are available for conduction. So that means by knowing EF of an element, we can exactly know how many electrons may be available for conduction. So that means lower the EF, better the conduction. The concept of EF is used in electronic industry while designing the junctions such as diodes, transistors, etc. Electrons from the materials with the higher energy tend to flow towards the material with lower energy. Hence, it helps to predict the direction of natural flow of electrons due to the formation of junction of dissimilar materials. This is what the importance of Fermi energy. Now let us learn the temperature dependence of Fermi factor. Okay, so that means this graph is shown for T is equal to 0 Kelvin, which we have already seen. At the energy levels below EF, we are having the field energy states, and energy states above EF are vacant. So this is for 0 Kelvin. This slide refers to temperature above 0 Kelvin. Previous one was at 0 Kelvin. Now this is above 0 Kelvin. So that means we have some different representation, graphical representation here. Previous one we had, this is what for the previous one we had for at 0 Kelvin, for 0 Kelvin here, but T at greater than 0 Kelvin we have in different colors. So we have the graph that is traced in this particular path. Okay, let us see how we can explain this. Here in a single slide I am giving at 0 Kelvin, and this is a higher Kelvin, and is the formula for f of t, wherein you see that f of t is depending on t. This is important. So based on this formula, this dependence, we are going to explain the different graphical representation. This slide is important, so concentrate on this slide. So wherein we in fact going to explain the dependence of Fermi factor with the temperature. Okay, so we are having basically we are having two cases, which is T is equal to 0 Kelvin and T is greater than 0 Kelvin. So at two situations, one at 0 Kelvin, other one is above 0 Kelvin. Okay, so first let us consider the first case, and let us say that IA, where in addition to 0 Kelvin condition, we have E less than EF. Okay, E less than EF. So now you have already seen this explanation previously in the previous slide. Now let me concentrate on the formula to explain the temperature dependence, because I already told you in the previous slide that f of E is depending on temperature. Let us try to explain that here. Okay, condition is T is 0 Kelvin and E is less than EF. So that means T is 0 Kelvin and E is less than EF. Okay, T0 means numerator is 0. So that means something divided by 0. But what is that something in the numerator? Sorry, in the numerator, yes. The numerator, that is E is less than EF. That means we are having some negative value here. In the numerator, we are having some negative value. So we are having negative value and we have 0. So that means it is some minus infinity. Okay, because some value by 0 is infinity, some negative value by 0 is minus infinity. So we have e to the power minus infinity. Okay, that is what is written here, e to the power minus infinity. Okay. So e to the power minus infinity means what? E to the power minus infinity is nothing but 1 over e to the power infinity. That also you can right? Okay, so 1 over e to the power infinity. 1 over e to the power infinity is nothing but 1 over infinity. So this is 1 over infinity. 1 over infinity is nothing but 0. So that here what we have is 1 plus 0 we have. Okay, so that means 1 plus 0 is 1. Then 1 divided by 1. So what is 1 divided by 1? 1 divided by 1 is 1. So that means f of e is equal to 1. Okay, so we have this result, f of e is equal to 1, where at e less than ef, which is naturally is a filled one, as you could see here. Okay, yeah, fine. Next, let us go for the next condition, that is temperature condition is the same, that is T is 0 Kelvin, but E is greater than EF. So that means here in the formula E is greater than EF. But what about T? T is 0. T is 0. So we are having E greater than EF, means we are having a positive number. So we are having some positive number in the numerator, and we have 0 in the denominator. Okay, so that means it is some number by 0. Some number by 0 is nothing but what? It is nothing but infinity. Okay, so what we have? What we have is that is 1 here, 1 plus infinity. Okay, 1 plus infinity. This is what you have it. E to the power infinity here, e to the power infinity. Then it is 1 plus infinity. So 1 plus infinity is again infinity, and we are having 1 divided by infinity is nothing but 0. So f of e is going to be 0. So this is what you have, f of e is equal to 0. So where do we have? We have it at e greater than ef. So that means we are having here e greater than ef. What is the situation here? Here the energy levels are vacant. That's all is the conclusion. Okay. Okay. So these are the first condition. I'm just putting it as 1a and 1b. Now let us go for 2a, wherein we are having T greater than 0 Kelvin. Before going, let me just erase all these things here in the graph, because I'm going to use the same graph for the next explanation. That's what I told you. Concentrate on this graph. This is very important also from the point of examination, as well as for understanding the f of e dependence with the temperature. Okay, okay. Now consider the case 1a. So wherein we have T greater than 0 Kelvin for condition E much less than EF. So when I say E much less than EF, that means I am considering almost in this region. Okay, so wherein E is much less than EF. Okay, fine. Let us go mathematical here in the formula. So this E is much less than EF, then we are having some negative number again. Okay, because EF is larger than E, then we are having some negative number. Okay, and T is not 0, but it is some number, and we are having a negative number here. So that means when you say that it is a negative number, it is in fact it is a large negative number. Why? Because we considered E as much less than EF, or EF is much larger. So that means the gap here in this formula is going to be very large. So that means it is a very large number divided by KT. Okay, so that very large negative number by KT is almost something like you have it here as e to the power minus infinity, something like that. Okay, not exactly, but something like that. Okay, but if you consider that, then what it is there in the previous ones, we had it as okay, e to the power minus infinity you had, then you had it as 1 over e to the power infinity you had, and then that means 1 over infinity is nothing but 0. So then it is 1 plus 0 you have. So that means it is 1 over 1 you are having. So 1 over 1 is nothing but 1 itself. So that means f of e is equal to 1. So in this region you could see that, if you see in this part, we are having the occupation or f of e is 1 only, almost 1 only. Okay, so that is almost 1 only. That is what is the explanation for the condition. Okay, now next let us go for to B, that is T greater than 0 Kelvin and E less than EF, that is just less than EF, or maybe we say that it is approaching EF. That means where we are now, in fact, I'll change the color. Now in fact we are somewhere here, E less than EF. Okay, maybe E is here and that is approaching EF. Okay, this is approaching EF, so that means we are somewhere here, we are speaking somewhere here. Okay, fine. So now what is it mathematically? Okay, so E, okay, let me again erase these things. Okay, fine. Here when we say that E is less, of course, E is less than EF. Okay, so that means anyway the difference is going to be some negative number, we have. So that means it is some negative number divided by KT. Okay, T is again a non-zero value, or some negative number by KT you have. Fine, and it is approaching EF. Fine. So as you see that E approaching EF, that means this difference is going to be smaller and smaller, but the difference is negative. So that means the negative number is going to be smaller and smaller, and it is e to the power of some negative number, right? E to the power of some negative number. You have to imagine here it is more than mathematics, this is bit logical. So what we have is e to the power of minus number. Okay, so that means we are having e to the power of some minus number, means we are having some fraction kind. Maybe we are having some fraction kind, but whatever that is going to be added here in the denominator to 1. So it is 1 plus something, we are having 1 plus some value. So that means it is greater than 1. So denominator is greater than 1 we are having. Okay, so then you are having 1 in the numerator, and in the denominator you are having some number which is greater than 1. Okay, so then what is that you have? You are having some fraction again. You are going to have the fraction for f of e. Okay, so then you are having that fraction is going to decrease with as the difference is going to be smaller and smaller between e and ef. So that is what you have. So that means the fraction is going to decrease here. You see, that is what is told as a decrease. It is going to decrease. Okay, so that is what you could see for the condition, that is f of e is decreasing. Okay, now let us go for the last case, that is 2c, which is again above 0 Kelvin, and E is exactly equal to EF. This is easy to understand. Okay, let me again erase all this explanation with the formula. I'm going because I want to use the same formula here. Okay, yeah, fine. Now let me use this ink. F of E, what we have? E as equal to EF. So that means E as equal to EF. So what do we have? Simply E minus EF is 0. So it is 0 by KT is nothing but 0. Okay, so 0 by KT is nothing but 0. So that means what we have is e to the power 0. Simply it is e to the power 0. So e to the power 0 is what? Or anything to the power 0 is what? Is nothing but 1, right? Okay, now 1. So what do we have here as 1? So what is we have in the denominator? It is 1 plus 1 is nothing but 2. So in the denominator what we have is 2. Okay, 1 plus 1 is 2. In the numerator we are having 1. So what do we have totally for f of e is nothing but 1 over 2 is nothing but half. F of e is equal to half. And that is what you see in the graph also. So at E is equal to EF, at E is equal to EF exactly, you are going to arrive at this point wherein f of e is going to attain the value half. That's all you have. So hence this is very important. Given also this in the notes. Read the notes. You will understand better. And this explanation is very important. Now let us go for another two definition. One is Fermi temperature and a Fermi velocity. Here the Fermi temperature. Fermi temperature is the temperature at which the average thermal energy of the free electrons in a solid becomes equal to the Fermi energy. Okay, so this is one of the definitions. So the wherein what we have is a temperature. If you say any temperature of a material, wherein the free electrons are also going to be present, and its thermal energy, if it becomes equal to the Fermi energy, then the corresponding temperature we call it as Fermi temperature. Another definition what you could see is the temperature at which the energy of the conduction electron attains Fermi energy. Okay, so whatever the electrons which are present above EF, what we say, which they are available for conduction, and energy of such electrons, if they attain Fermi energy at some temperature, it is not at 0 I am speaking, at any other temperature, then that temperature is called as Fermi temperature. Okay, so then if you just approximate T is equal to TF, then the energy, thermal energy, what we define as KT, that KT will be equal to KTF, that is nothing but EF. So KTF, that is Fermi temperature, is equal to EF by K. Okay, just give K is a Boltzmann constant. If you just consider sodium, for which EF is 3.2 eV, converting it into joules and substituting in the formula with the Boltzmann constant, you are going to get EF as a very high temperature value, that is 37,000 Kelvin, which is very huge number. The difference is mainly because only a small fraction of free electrons are present in the Fermi level. Okay, so that means not that all the electrons are present in the, or because what we calculated previously is for the entire electrons, but it is not necessary that only if a small fraction is going to be present in the Fermi level. So material temperature means what? Material temperature means it is average temperature of all the free electrons. You see that, of all the free electrons. But in quantum free electron, we say that we don't take all the free electrons. Okay, only few, statistically only few. Hence, material temperature is much less than that of the few electrons present in the Fermi level. Next, let us see the Fermi velocity. It is very simple. The velocity of the electrons which occupy the Fermi level is called Fermi velocity. That's all. It is as simple as that. Velocity of the electrons which occupy the Fermi level is called Fermi velocity, and it is denoted as V suffix F. Okay. Of course, it is maximum velocity that an electron can attain. Okay, and the formula is given by Vf is equal to root of 2 EF by ME, wherein we are considering the kinetic energy equation previously. You could refer here. And again, if you consider sodium with EF as 3.2 eV and converting it into joules and substituting in the above formula, we are going to get Vf is equal to 1.1 into 10 to the power 6 meters per second. In this slide, I have just tabulated the values of EF, TF and VF for a few of the metals, as you could see, lithium, sodium, copper, etc. And for this one, we are having EF value here. For lithium, it is 4.76. Some of the important things is copper, it is 7.05. This value is important for you because you have an experiment also in the lab to find the a Fermi energy of copper. And for silver, you see that it is 5.49. For gold, it is 5.52. Okay, and these are some good conductors. These are the good conductors what we have. And we also have a value for VF, that is Fermi velocity and the Fermi temperatures. Okay, just look at this table for you to have some correlation. Okay, finally in this lecture, in this class, let us see the significance of Fermi energy. What is its important? There are two parameters for this you need to concentrate. Electrons from the materials with the higher energy tend to flow towards the material with the lower energy. This is a natural flow. This is what we are having as a natural flow. So that means if you know a material which is having a higher energy and which is having a lower energy, then you can predict the flow. How is the flow? The flow is to predict the direction of the natural flow of electrons due to the formation of junction in dissimilar materials. Okay, so EF is used, the value of EF is used to predict the direction of natural flow of electrons. Okay, so this is as I mentioned previously, it is mostly used in electronic industries, mainly for the design and construction of diodes, transistors, etc.